Congrats on the first. Anders has gotten a few firsts. Oh, you're nearly on the board though. You only have one first, $10? I guess you usually don't care to redeem it though, I guess. That's probably why. You definitely have been the first in chat. Your fair share. Okay. What am I forgetting? I'm forgetting. Just boiling the ketty? Okay, boiling the kettle? Sounds good. What command? I made a command for this. I can't remember what it's called now. Hey, Sandculp. Hope you're doing well. Why would I make it? No. Wait, what is exclamation point GR pin? It is that. Do I not know how to set up commands? Why isn't it is GR pin? Hey Ashu. What? Is a different command? Wait, the first command worked. Sorry, this is gonna bother me. Why? That one works. I set it to the wrong thing. Okay. There we go. Okay. Now that I have that figured out, I'll hop into Discord. Fenbox will be here soon. Okay, but yeah, chapter 7, the description of curved spacetime. It's pretty mathy. Okay, good. I'm on open mic on Discord. While I wait for Alex here, I'm just gonna kind of scroll through the chapter, figure out what the first place I wanted to talk about was.
Hi, Don.
Oh, hey. How's it going?
Doing good. Yeah, having a good day. How about you?
Nice. Pretty good so far. It might get a bit worse depending on how this goes, but
Got to keep reminding ourselves it's only for fun.
Yeah, exactly. Okay, so did you have a chance to get through the rest of the chapter, or I know you've gone through at least most of it?
Basically, I got like 2 pages left. I got up to the last section where they were talking about 3D surfaces in 4D space-time.
Okay.
And I was up to the example where they were talking about the hyperbola. So I almost got there.
Okay, and I have gone through the end, but it was maybe like 2 weeks ago, so it might be a little bit. All right, I'm gonna have to like look back through the chapter for what they were doing, but I'm just scrolling through to remember the interesting bits that I wanted to talk about. Overall, with the summation convention stuff with the indices, I don't get why we need it. I assume things will get more complex later, but like this feels like a lot of trouble just to avoid writing out a 4-vector or a 4x4 matrix. Or a summation, I guess. Like I feel like the things we're working with aren't that big, so I don't know.
Yeah, well, I guess we'll see.
Yeah. Okay, so the first thing that I was having a hard time wrapping my mind around is equation 7.13 on page 141.
Hmm.
It's the mathematical statement that you can always find local coordinates that are that are perfectly flat for, like, you know, that very small local bit of space, an infinitesimal neighborhood at a single point P. And
Right.
the thing about this that I didn't get was if your metric G depends on the point, or or sorry, if the metric G ends up being equal to the constant like Minkowski metric eta, like that's just a diagonal matrix with the -1 and the ones. Wouldn't the derivative of that thing already be 0? Or I feel like the second condition isn't actually adding anything if the first condition
Oh.
already covers that things are constant. So I don't really get that.
Oh. I think I understand what you're saying. The way I see it is it's kind of like finding a tangent plane to a surface in 3 dimensions, right? So
Yeah.
you could say that, so if you had like, I don't know, let's say like z equals x squared plus y squared. Yeah, that's a good example. Let's say we had z equals x squared plus y squared. So what's that, paraboloid?
Yeah.
So obviously at the origin, we've got a tangent plane, right? That's got partial derivatives equal to 0 at that point 0. But the first order partial derivatives of that function are not 0 everywhere, right? Like they're, oh, well, wait, I see what you're saying. You're saying because they already are 0. Okay, I think I see what you're saying there.
Yeah, I think what you're saying is probably like the right thing. I just thought it was already being said, I guess, by the first thing. So I'm not sure what this is doing for us. Hey, mouse.
Yeah. Yeah, I thought I understood that, but now you're making me realize I don't really understand that. Maybe it's okay. So the second part of equation 713 is telling us that that in my analogy, it's kind of like saying that the partial derivatives are equal to 0, right? Partial dz dx and partial dz dy are both 0 at the origin in that example I was talking about. So what's the first part of equation 713? What's the analogous way to think of that, I wonder? Well, okay. Would it be, because I'm thinking of G versus eta as some kind of a stretch, but I guess it's not really just a stretch.
It is some type of transformation.
Yeah, transformation. Yeah, I don't know.
Yeah, because like there is some sort of analogy with linear algebra and like converting bases and stuff, but this it's a little bit different here. So I've been trying not to think about it too much in linear algebra.
Well, how about this though? How about this? So the G metric is equal to the eta metric at a given point, right? Or we can find a transformation such that we can make them equal at a given point in space-time. But that doesn't mean that, I want to say that doesn't necessarily mean that like all the partial derivatives of G with respect to the vectors would actually have to equal 0 at that point, right? Like you could plug in some numbers and get minus 1, 1, 1, 1, but maybe you could do that without the partial derivatives having to equal 0. Does that feel like it's possible?
Oh, maybe.
Did they do an example like this where they because I know they
I
were
think it's
talking
supposed to be
about like the
7.2
second
right below.
derivative. Oh, is that where it was? Yeah. That's right. That's right below it. Because I know they talked about like the second order partial derivatives representing some kind of a curvature, which I thought
Right.
sounded really neat.
Yeah.
But I guess that's not coming until like chapter 20 something.
Um. Okay, yeah, it's the paragraph right after that example, chapter 21. The second derivatives are the measure of spacetime curvature at a point. And I think we learned about at least a version of that, or at least that, like that's something that's sometimes covered in like a multivariable calc class, like kappa, the idea of curvature.
Yeah.
I assume that it's like an extension of that.
Yeah. Probably something we'd know more about if we'd studied differential geometry.
Yeah. Streaking.
What's Poison Mouse blaming me for?
I don't know. Um,
Did you do example 7.2? I mean I read it, but I didn't do it very carefully. Like I didn't see how to derive the G matrix there.
I didn't like do it out on paper. I felt like I understood it when I read it though. Existential blaming mouse says. Okay. Um,
I feel like we probably could work that out, right?
yeah, they were just
I
doing
think those are
some.
just they're just partial derivatives, aren't they?
I want to say so, yeah.
It's a function of x and y. So what is it? Is it partial d phi dx, partial d phi dy, and partial d theta dx? Is that what they did? Hmm. Oh, and then no.
Wait, yeah, it's G a matrix
Or
of the partial derivatives. I'm forgetting now. Oh, it's just the coefficients of whatever's in front of the dx's.
yeah.
Um,
Yeah, well, we could come back and look at this later if you want to.
okay. Yeah, I assume they took derivatives of those conversion equations and plugged it
Yeah.
back into the ds squared equation.
Yeah, that's what they said. They said they're going to substitute it back in the ds squared.
This is link in a Stack Exchange thread. Let me just look at it quickly. Oh, this might be a calculation for the thing that we're talking about. But I think I might like work through the math for myself though, to be honest, if we do that. But thank you for finding that mouse. Okay. So I'm going back to scrolling through the chapter. You are the best mouse, yeah. Okay, so like example 7.4 on page 144, I thought it was kind of interesting that they use the warp drive spacetime as an example of something when it's not really like realistic. I assume there's a reason for that. Like maybe the realistic spacetimes are too complicated, but it was kind of interesting to me that they kept kind of coming back to this, to like more unrealistic spacetimes with warp drives and wormholes and stuff. Ben, Hope you're doing well, dude.
Yeah, when I started reading 7.4, I thought I wasn't going to have any idea what was going on. But the more I read it, the more I sort of felt like I kind of understood what they were talking about.
Thank you so much, Ben. I'll see you around. I appreciate it. Uh, yeah, I could sort of follow 7.4. There's a lot going on with the functions that they're defining.
Yeah, I know.
Sounds good, Mouse. See you around. Okay, but continuing to scroll. Learn how to calculate area in volume.
Yeah, what did you think of 7.6? I was really happy with 7.6. I felt like I followed all of it.
Yeah, I don't think this one gave me too much trouble. I feel like I would have trouble doing this for myself with a different line element, but I could follow the work that they were doing, or I wouldn't feel confident, I guess. But I did see there was one of the questions I chose was to calculate the area of that peanut back in chapter 2.
Oh, okay.
So, and
All
I
right,
think there's
cool.
at least one other one that was like this. So
Okay.
we'll get some practice with that. And then they looked at the wormhole space time. That one, this was a kind of crazy example of how they figured out how the space time looks.
This one I would not have been able to do myself. I mean, I understood what they did as I read through it, but yeah.
Yeah. Um. This one, I'm definitely missing something. I feel like I can understand the individual stats, but like the kind of big picture of it is still a little bit like lost on me.
Feels like a lot of these questions are are about finding good ways to transform from one geometry to another.
Yeah,
Or
they
like a
did do a few
or like
like
a
changes here.
yeah. Actually, they said that in example 7.3 now that I look back at it.
Some
Yeah, on page 143. Yeah, this one. And right at the end, they said this metric 720 is really just flat space in a different system of coordinates. Can you find a transformation that puts it in the form that we're used to? And I thought about that for a while, not too long, but I thought about it for a while, and I couldn't come up with one.
I thought about it for like a minute and then I gave up.
I, I don't know. It felt like it probably shouldn't be that bad.
Yeah, like I was guessing something obvious, like maybe t equals 1 over x or something. I
Hmm.
didn't really like pursue it though. Um, okay, well, maybe that's worth like writing out. I feel like it should be something. I just went over to the Excalibur. That's my thought with the 1 over x thing is that if we take. Oh, wait, is this how we. That doesn't make sense to do that. Wait. Never mind. We I feel like we need to do 1 over something, but making it 1 over x feels like it doesn't make sense.
They said
Um,
the light cones had slopes of 1 over x. And I was trying to think of that too. Like if the light cones there have slope 1 over x, and in the other one, the light cones just have slope 1.
right. Um,
Could it be just some stretch in the x direction? It feels like, no, that's not going to work, is it? No, it doesn't work. Is it like e to the x or something? X, capital X is e to the x? No.
I don't even know what variables we're supposed to use here, to be honest.
No,
Uh,
I don't either. I don't either. But I think we want something like, xt. Oops. Some way to get back and forth to like this.
oh yeah, okay. They they are asking to put it in lowercase letters. So we would take
Yeah.
small x equal to something, small t equal to something. Okay. So, hmm.
Yeah, this may be one where you just kind of see it or you don't, and I don't.
Yeah, like I'm trying to guess that like small x should just equal x, and then like uh maybe small t equals like 1 over big X times big T or something.
Yeah.
I don't really know because this is going to end up being a product rule, and I don't know if it's going to get us what we want.
But it has to satisfy this.
Yeah. Uh, yeah, I have no clue. This is all sorts of messed up what I'm suggesting here. So yeah, I don't know.
Yeah, well, that's cool. Let's just keep reading the chapter, I guess.
Yeah.
Going over the chapter.
Um. So stuff on the wormholes, vectors and curved spacetime. This part, honestly, this part was a little bit upsetting that like vectors just don't work anymore, really, or they only work in very limited like circumstances.
Oh, that's right. Yeah. Displacement vectors must be abandoned. Position vectors must be abandoned.
Mm-hmm.
Hmm.
And so you can sort of save it, I guess, by thinking about the tangent space, which they talk about, but feels like sort of a hollow victory because you can't really compare vectors at different points, as far as I can tell.
So do you think that in that picture where they have the flat tangent space and they have the curved space time, do you think that's the case where in the curved space time you'd have like the G metric and at point P you could kind of linearize it with the eta metric?
That's probably it. I think it's relying on that idea.
Yeah. Because one thing I did notice in the last couple of sections here, and even earlier in the chapter, is like really feels like linear algebra, doesn't it? Like a lot of this stuff feels like kind of like linear algebra to me in some sense, anyway. Especially this stuff with bases that we're about to look at.
Yeah, it nearly is. It's just that there's this annoying minus sign that comes up for the time component. And I feel like they're pretty careful of specifying 3 vectors versus 4 vectors, but they never even mention, or they never address how the dot product is different from the usual thing. And they're not really careful about what like the dot product they're referring to is at any particular time.
Yeah, I think I did feel like this section was going to rely pretty heavily on chapter 5 stuff.
Yeah. I do wonder if this, sorry, if this tangent flat space idea is another thing of, or it's like an expression of the equivalence principle.
Mm. Yeah, probably.
Yeah.
I didn't feel like I actually understood the dot product even in chapter 5.
Yeah, like yeah.
In chapter 5 they actually sort of introduced all this, and they were using all the superscript subscript notations. I really got to go back and read that again now.
Yeah, I definitely went back and read when they first introduced it, because they just kind of expect you to remember it. Tyler, it's funny, this book actually has a section where it addresses flat earth stuff a little bit. But hey, on a small enough scale, you can find a set of coordinates where the earth seems flat for an infinitesimal neighborhood around that point. So, you know, there's something to that. Hey, ADS. Wait. They talk about orthonormal bases. And coordinate bases. This is where so I think a coordinate base is a, like an orthonormal basis is a special nicer case of a general coordinate basis.
Yeah, that's what I want to think too.
And this is the thing I was talking about the other day, where on page 156, under the header working with coordinate and orthonormal bases, kind of the end of the first paragraph, which is, we calculate in coordinate bases and interpret the results in orthonormal bases. I don't really know. I don't know. I don't really know how to interpret that, like what it actually is going to mean.
No, I read that a bunch of times, and I tried going through box 7.3 where they were talking about a possible 5th dimension, a tiny little unobservable curled up circled dimension that we don't know about.
I might have. Oh my god, did I not even read that one?
It was on page 157. Yeah, this thing.
Oh. I mean, I think I skipped past it, intending to come back to it, and I never did.
It wasn't very, I didn't feel like it was really very, it didn't really elucidate it. Yeah, it didn't help me to read it.
Hey Sage, I'm doing well. How about you? Yeah, I know all the previous boxes have been not super helpful in talking about things that I haven't even come close to learning about yet.
Yeah, I just read it because I thought maybe it would show me what the difference was between calculating versus interpreting results, or the different bases, but I didn't feel like it helped me.
Okay. Yeah.
But if you look at equation 760 or 759 and 760 on that right there, don't they feel like, doesn't equation 760 remind you of in linear algebra where you learn about, having two different bases for a vector space, and you learn about some kind of transformation from one set of, from a, a representation of a vector in one of the bases to the other one, and there's like a set of transformations that get you from one to the other. As I remember, they had this similar kind of notation. They had like subscripts for the basis vectors or something, and I always found it really confusing and hard to understand, like what the notation meant. And this reminded me of that.
I think it's the exact same thing, yeah, where
Yeah.
the scalar components of each of the basis in the old basis vectors that you take in combination of are the coordinates in the new basis. I think that's what these equations are saying, set 760.
Yeah.
Oh god, Sage World, I hope you get some good sleep. Um, thanks, Sage. But yeah, after that, uh, I only sort of followed pretty much everything after this.
Yeah, I
I
was reading this section today.
okay.
7.9.
Yeah, it's just gotten super weird here.
Well, it feels like you're taking the four-dimensional space-time and you're just kind of like, what are you doing? Like modding out one of the dimensions or something.
Yeah,
It's like a tangent plane to a surface in 3 dimensions, right? That's just how I'm thinking of it still. But except it's a tangent space to a four-dimensional whatever.
yeah.
A tangent space.
I guess it
Yeah.
basically like level curves, but the curves are now three-dimensional surfaces.
Yeah. Yeah, like these pictures you're looking at on screen right now. I think each one of those slices is really not, it's not a two-dimensional slice, it's a three-dimensional slice. It's just that they can only show it as two-dimensional on the page.
Yeah.
What about this one with the hyperbola? I really want to understand
Hyperbola.
that because I tell you, since we've studied this, I'm fascinated with hyperbolas. I want to know more about how they work. Ever since I saw that Lorentz transformation, and they were talking about hyperbolic angles, I'm like, I want to know what these hyperbolas are doing.
I don't think I understood anything they were doing with this hyperbola.
I sort of understood that it's a representation of negative t squared plus r squared equals negative a squared. That made sense. But then they said the unit, let's see, what did they say? I'm looking at that graph there, figure 710.
Mm-hmm.
A sequence of equal length time-like normal vectors is shown at equally spaced values of chi. These are not normal to the surface nor of equal length in the geometry of the plane, but they are in the geometry of space-time. And what do they say? Each point on the curve corresponds to a two-sphere. And I think I know what that means now. It means like a two-dimensional spherical surface in like the surface of the Earth, right? That's like a two-sphere.
Yeah. I think so.
Each point on the curve corresponds to a two-sphere containing the other directions in the surface, those along theta and phi. Okay, but I don't know how to calculate those normal vectors.
It's probably something from chapter 5. something.
They got
I'm
it
not
on
quite
page
sure.
162. I just didn't get this far. The
Oh,
last couple of pages, I didn't read it.
what's the concept, Shreya? Yeah, they also got null surfaces.
Yeah.
And then that was the end.
Yeah, I didn't read about null surfaces.
Okay. If you want me to just get into the questions, then I guess, because I don't think I had much to say about them.
Yeah, sounds good.
Okay. Unit vector, Shreya. If you want, we can talk when I'm doing kind of general math help, but right now I'm doing a reading group. Okay, I think we can just get rid of this math with the...
Yeah, you want to wipe
with
that?
that.
Yeah, cool.
Yeah. So the first one I grabbed was number 1. I grabbed equation 7.7 and the context around it. In the singular line element for the plane 7.7, show the distance between r prime equals 0 and a point with any finite value of r prime is infinite. So Serban's I don't feel qualified to answer that question. And right now it's not like a question answer part of the stream. We're just trying to learn about general relativity. I don't know much about kind of finance like that, so
Time value of money.
oh, okay.
Yeah, I learned some of that when I was taking some of those actuary exams.
If I was to guess, I'd say you can probably do more with that 84,000 in 2 years than you can with a little bit of extra money. I guess in total it's only a $6,000 difference, right? For that's your work for
Yeah.
waiting 2 years, so it seems like
Yeah,
just
there you
take the
go.
money now.
So the question is, can you make $6,000 in 2 years on an 84,000 investment?
I guess I don't know how reasonable that is, but I assume that someone can do it.
Yeah, I don't know. If you're good at the stock market, then you can do that. Yeah.
Yeah, as long as it's a good 2 years, I guess. It's not too simple, Servants. I just don't really know much about financial math, especially if you're... I don't know if this is hypothetical or if you're actually asking for advice, and
Oh God, yeah.
I don't want to give someone actual advice because I don't know what I'm talking about.
Yeah, don't ask me either. I always like advising students at college on like academic stuff, but as soon as it's something to do with financial aid or whatever, I'm like, I'm not touching that.
Yeah.
Please don't talk to somebody else. Like then it becomes a little more serious.
Mm-hmm. Yeah, if even 5% works out, then that seems like the better thing to my eyes. Anyway, so for number 1 here, I assume we're gonna do an integral with the square root of that 7.7.
Yeah, yeah, that's what I would think.
From 0 to some arbitrary finite value a, I guess.
Okay.
Um, oh wait, they already use a.
Oh yeah, good. Yeah, I didn't even see that.
Maybe I'll say, I guess b.
Yeah, why not?
A to the fourth over r prime to the fourth dr prime squared plus r prime squared d phi squared. The bounds. I might be premature in putting the bounds on this. We haven't decided what we're integrating in terms of, right?
The distance between r prime equals 0 and a point with any finite value of r prime. Oh, I see. Because part B, we're going along the line phi equals 0, but in part A, they didn't tell us. So we can't really assume. Yeah. Oh, wait. But r prime equals 0 is like the center of a, well, that's the origin, isn't it? So actually, we could go out along a straight line, couldn't we? Can we choose that? Can we just choose to go along a straight line to any other point?
Uh,
Hmm.
I would think so. Servant, so
Yeah, because the whole
okay.
idea of these metrics is it's supposed to be independent of which. No, no, that's not true. I was going to say it's supposed to be invariant, right? Like if you integrate from r prime equals 0 to any other point, isn't it supposed to be invariant of which way you go? Except now I'm thinking back to chapter 4 where we had the 3 points in the triangle and it mattered which way we went.
Yeah, it's like we need to figure
Hmm.
out the shortest path and show that's infinite.
Oh, okay.
But I don't know how we do that. I feel like we haven't learned that.
Well, if you look at that integrand, wouldn't it just make sense that letting d phi be 0 would give us the minimum value there? I feel like it would have to.
Mm, I feel like we're going to end
This,
up just
yeah,
letting dphi be 0, but I don't know if that's
yeah,
the
because you
reason
know
why.
what? This is a D capital S. Yeah, remember I mentioned this the other day in your other stream.
Oh, yeah.
One thing I noticed in this chapter, and I went back to the other day and looked at chapter 4, and sure enough, it was hidden in a little footnote, and it said that in general, the notation they're going to use is when they use a lowercase letter, it's going to stand for a space-time um, quantity, and when they use an uppercase letter, it's going to stand for just a space-like quantity. So what we're doing here is we're just looking at the space-like distance between these points. We're not worried
Mm.
about time, I guess, at all right
Yeah, there's
now.
no subtraction. Going along, changing phi would only increase the distance.
Yeah, that's why I pointed that out
Okay.
because there's no hidden negatives that we have to worry about here, right? I think. I hope there's no negatives.
um, Servants, the thing with stream is I generally take people's math questions, do my best to answer them like homework questions. On certain days, though, I do reading groups about general relativity or complex analysis. And that's what you're seeing right now. So I'm gonna be a little slow to respond to chat, and I'm not necessarily doing just like general question and answer right now.
Oh, Don, check it out. You don't need this because
Oh, I don't know.
this
I
is
shouldn't have
yeah.
put that. That was actually incorrect. Yeah. uh. Okay, and then that integral is easy enough.
Yeah.
Don't mess this up. It's gonna be 3 on the bottom. -3. Oh wait, no,
No,
I
no.
messed it up.
You jinxed yourself.
Yep. Okay, I think that's better. I mean, I guess I should say the limit.
Yeah.
As some dummy variable t goes to 0 from the left, a squared over t, and that's just going to diverge to infinity.
Wouldn't it be 0 from the right?
It sure would. Okay. I
Okay.
think that's good for a.
Yeah.
And then
Now you've already done all the work for part B, right? Now we can just plug in those numbers basically.
I guess so, yeah. Hey, Phobos.
Phobos, g'day.
G'day, mate.
I can legitimately say g'day because I used to live in Australia.
Yeah, I know mine is legitimate.
I used to say g'day. When my dad calls me on the phone, he still says g'day.
Oh, that's nice.
Yeah.
There's definitely some squiggles that are happening here. Just a squared over 5? What?
Now I'm trying to remember what the A stood for.
Yeah, this is...
Oh, it's just some constant A.
This is just flat space-time in polar coordinates. Like it's been transformed. Theoretically, we could do a regular integral in polar coordinates and get the same result. Like there should be some type of... This distance from 5 to infinity should represent some finite distance in regular polar coordinates. I don't know what it would be, though. But was also, I mean, you didn't know this about Fembox in Australia? A squared.
Yeah, I went to college and I did my college in Sydney. That was where my illustrious, education happened. Except I wasn't very much of a student back then. So I'm trying to make up for it.
Yeah, it's kind of the same, but that's kind of like same here. So this is like an inversion. Like,
Yeah.
if we're a squared, I guess represents it's some scale factor for the inversion. You dropped out, Phobos? I didn't know that.
I dropped out like twice.
Oh, wow.
Yeah, I dropped out twice. But I went back, but I enrolled 3 times. So I don't know. I changed my major twice. Yeah.
I dropped out of a master's like 5 years ago or something, but that was for software engineering. God, that was 5 years ago. You ended up finishing yours, Phobos, 8 years later? Oh, nice. I bet the integral from 5 to infinity in regular polar coordinates is just going to be the integral from like... Well, actually, we don't have to wonder. It's just... we could rearrange it to say r, well, actually no, we would just plug in 5 and infinity. If r prime equals 5, r is 8 squared over 5. And then if r prime equals infinity, r just equals 0.
Oh, well, now it makes sense, right? We just went from the center out to a squared over 5.
Oh, yeah, duh. Along the positive x-axis. Okay.
Yeah, this question felt kind of weird.
I guess it's just, yeah, I don't know. I guess they're starting us off easy.
Yeah.
Next one I grabbed was number 2.
Oh,
It'll
here
also be
we
a
go.
coordinate transformation.
And we have to find it.
Okay.
Oh my God, it's got a product of dx times dt here.
It does. It feels a lot like there's a difference of squares, or like there's gonna be like a plus dx squared minus dx squared thing, because this just looks like some version of like dt squared, or just dt plus dx squared. That's just,
Oh, wow. Yeah, you got it. That looks good to me.
I'm not quite sure what to do, because we need to deal with the minus sign, and we need, and this isn't exactly, I don't know what the actual coordinates are yet, but that's where my mind is going.
Yeah, that's great. I think you got it. That looks like it'll work.
Well, I don't know what the next step is.
Well, okay, well, I think it's just, let's see, we just do some algebra and mess around with it, right?
Um, Probably, yeah.
Yeah, yeah, your idea was great. Yeah, plus dx squared minus dx squared, right? That's what you said. Okay.
Um,
Minus here? Yeah.
yeah.
So let's do that.
This
And
explained. I'm
here,
not
this is,
taking questions right now. I'm sorry.
let's see. This, right?
Oh, so this should tell us like the the different variables we should take, I guess, like, or nearly. Like, we use capital letters for the transformed coordinates.
Yeah, so could we call, yeah, so we kind of want to call this thing in parentheses D capital T or something, maybe. Like set this equal to something like this, maybe.
Hmm.
So what about T equals T minus X?
We might need like a cubed, or
Cubed, you're saying?
or like for the differential to work out. How does this have to look?
Yeah, I didn't understand why we would need a
Oh
cube.
no, I think you're no. I'm sorry. No, this is fine. T minus x is perfect, I think. I forget we just square it as part of the thing. We don't need to.
Yeah, because I want the thing inside the parentheses to be the dt. So if I square it, I just get d capital T squared there.
Yeah, no, okay. I think this is just like the answer here, and everything else we can just take the same.
Like this.
Yeah.
Or I should be using, maybe instead of, I'll tell you what, instead of these capitals, we should be using primes, shouldn't we? That's how they've been doing it.
Yeah, primes is a good idea.
So I want this to be do you think it works?
I think this is perfect. I could bring up the solution key if we want to check it.
Okay.
That feels
If
good.
you're happy with it.
I just remember that I forgot to bring up the solution key, but I think this is just fine.
That was a good idea. You know what? That was a good idea. dt times dx. Yeah, it's like completing the square on those two.
Yeah, I only thought of it because the complex analysis, some of the problems required like similar tricks
Yeah, right.
to figure out the function in Z. Oh wait, so I didn't look at the solution. It's
We got a sign
they
wrong,
do
I should say. I
a
got the sign
plus,
wrong.
or they're arranging it differently.
dt square. I may have made a mistake with the signs, but I thought I had them set up okay.
Watch some biology. I think I'm okay, Sam. Bob was saying it looks good.
Maybe it doesn't matter if you shift it left or right, or if you add or maybe you could do a plus or a minus. Or did they just screw? Oh wait, they've got something on the solutions there in the middle there. Oh, is that where I made a mistake?
No, I think we could rearrange our equations to match theirs, I think, because x and x prime are equal to each other.
Oh, I see. They've got lowercase on the left and they got the primes on the right, but I put the prime on the left and the lowercase ones on the right. Oh, okay. So
But I think
what if
it's
I
fine. Like
just,
this rearranges.
yeah, you want to rearrange? Let's rearrange
Like
it,
we can
right?
take
So,
your top equation. Okay, yeah.
yeah. So obviously the bottom ones all work. Oh, I'm doing it the same way. What am I doing? I'm doing exactly the same thing. And what about the top one? So we get t equals t prime plus x, right?
And then x is x prime.
Yeah,
So we
because
did get the same answer. It just looks different.
from here. Okay. Oh, okay, cool.
Yeah. Okay.
Nice.
So far, so good.
Since you got the solutions open, you want to look at number one and see if we got it right?
Yeah, sure. At least integrate from 0 to r prime. But they don't even bother using a different name. Looks like we got part A right. And part B.
Another way to see this is that it's just the distance from r equals 0 to r equals a squared over 5 in usual polar. Nice.
Awesome.
Wow. 2 for 2.
Yeah. Next one is number 5. There's a bit more going on. So we have this two-dimensional space-time, which have coordinates v and x. We have to calculate the light cone at a point v comma x. And I think they're doing this by letting ds squared equal 0 and solving that, equation.
Oh. Yeah, okay, light cone, because it's the null cone, right?
Yeah.
Nice.
And ooh, is dividing out a dv bad?
I would just factor out a dv.
Okay. I mean, that's not going to make it separate. I want to separate it, I guess. Like I don't.
Well, you could say either dv equals 0, or you can divide both sides by dv, I guess.
Yeah, I guess if dv equals 0, are we just going to say that's uninteresting and we're not going to consider it?
I don't know. What is v? It's not. We're not supposed to think of it as a velocity, right? They just said it's two-dimensional space-time.
Looks like it's playing the role of time. It has the minus sign in front of it in the line element.
Okay.
I think when we look at the solution key, they're just gonna divide out that dv and not care about it. But I don't see how else we would solve it if we can't get this to be like first order. Or yeah. So we would end up with dv equals 2 over x dx, and now we can integrate.
Yeah, okay. Oops.
So the question was to calculate the light cone. I assume we set c equals 0. They've kind of been glossing over that. Or it's like the place and saying, you know, we make it coincide with 0, 0. So is this calculating the light cone at v comma x, or do we need to do something more?
Well, okay, part B says draw the picture. So because that's kind of what I was thinking, like what would this look like? Okay, I see. It's that picture you got on screen, figure 7.1. So we got to think about those light cones there.
Yeah, they just did it as a slope field, but they got basically the same. Oh, it's plus or minus. Oh, or is it? Maybe this one isn't plus or minus. No, we do have a slightly different situation. They have plus or minus because they square rooted each side. We didn't square root each side. But other than that, like they have almost the same differential equation. We just only have the positive case. So I think it's going to be really similar. We just are only going to have ooh, wait, what the hell? There should be a plus or minus.
Is there?
Or they say somewhere that I don't remember if it was here or somewhere else, but they say like the plus or minus reflects that there's two different directions light rays can travel or something.
Oh, they did? I'm not remembering that. Are you talking about like the future light cones and the past light cones?
No, so like the plus makes up one border of the light cone, the minus makes it the border of the other light cone. We do have an absolute value. I wonder if that's supposed to make the difference.
Well, we did factor out that dv, right? Because I mean everything was kind of two-dimensional until we threw out the dv and made it
Oh, does that make
like
up the other border?
one-dimensional.
Lines of constant V?
Yeah, maybe.
Okay, well, space-time diagram.
Yeah, let's try and work out what it looks like.
So I think we're definitely getting some type of logarithmic, like, null lines. Um, now, because it's absolute value, I mean, I don't know if they're just going to ignore that it's the absolute value of x. They didn't care about it in the example they did, so I wonder if it is the lines of constant V.
Well, maybe we don't have to worry about x being negative in our picture anyway.
Yeah. So I guess a
But you're
light cone might
but
look
you're
like...
talking about the slope, right? Oh, I see. Because the light cone has to have like a left side and a right side.
Exactly, yeah.
Hmm. So how do we get a cone shape? You're saying that orange thing there?
That's the only thing I can think of, yeah.
So tipped over light cones reminds me of the warp drive.
Yeah. And they would get... They're narrower, closer to the origin, and wider, farther away, I guess. I probably didn't draw all these green lines accurately.
Yeah, they look pretty logarithmic.
But yeah, I don't feel that confident in this.
Yeah, I know, me either. It seems kind of weird.
Yeah. What does part C say? Show a particle can cross from positive x to negative x, but cannot cross from negative x to positive x. Oh.
Oh, well, all right. We do have to worry about negative x then. Oh, okay. Oh. So if x is negative, then we get the negative slopes, do we?
Um,
So the whole thing's like a mirror image in the v axis.
yeah, but I get C's giving us a hint about how the light cones should look, right? Because The light cone
Yeah.
needs to be pointing a certain way. I guess from positive to negative.
Okay.
So maybe we should get rid of this graph that I drew.
Oh, you didn't think it was right?
Well, not maybe I should shove it to the side and put a negative x-axis on here.
Yeah. Can we flip it? Can we reflect it and like? Is that something you can do with the tools up here? Like make a mirror image?
Oh, I'm just doing it by hand.
Cool.
Um, but if a particle can cross from positive x to negative x, uh, shouldn't my light cone be pointing the other way? Saying called. It's not my birthday. I don't know who you're saying that to. What's the like? What is the orientation of these? Oh well, okay. Increasing v is in the future, and so I assume we care about where the future light cones are pointing. Which means they're still pointing the wrong way. From positive to
You know,
negative.
wait a second now. We have this whole question is talking about a two-dimensional space-time.
Yeah.
So if it's two-dimensional, that means you must I guess you have one time axis and one space axis.
Yep.
So then what does a light cone look like? I mean, I'm struggling to understand what that even would look like. Would it just be a one-dimensional light cone?
Oh, I guess it would be, yeah.
Calculate the light cone at a point Vx. I mean, we still have two dimensions. A light cone. All right. Okay. You can hear me flipping pages. I'm in chapter 4. The locus of points that are null separated from a point P in spacetime is its light cone. Well, that's exactly what you did, right? You set ds to 0.
Yep. And so that gives us the border of the cone.
And then it says here, well, the light cone of P is a 3D surface in 4D spacetime, but I guess not for us, not for this question. The future light cone of P is generated by light rays that move outward from P. Past light cone of P is generated by light rays that converge on P. You can think of the future light cone as the surface swept out in spacetime by a spherical pulse of light emitted from the location of P at the time of P. Okay, and in our case, I guess a spherical pulse is just a one-dimensional. It's kind of just like shining a flashlight in two directions at once, right? Like on a line.
Yeah, I think so.
I'm confused by this V. So I'm just going to think of V as time.
That's
Why
what
would
I'm
they call it
doing. It
V?
has the minus sign.
Yeah. Okay, so V tells us what time it is. X tells us where we are on our line. And what we came up with was dV dx is 2 over x.
Phobos, I think so, yeah. Hey, Sharia. And see you, Sandcult.
If a particle could cross from positive x to negative x, but cannot cross from negative x to positive x, I'm kind of using what they say in part C. I mean, I know we're supposed to prove it, but let's just assume that's true. What is that? What can that tell us about like part A and B? So as time increases, that means we can only move left. I guess that's what that's telling us.
I guess so, yeah. Sharia, this is like undergraduate physics that we're looking at. Okay, so I did just remember in the part that you didn't read, in figure 7.11, page 163, the caption says, a tangent vector t is shown. Null surfaces like this one have a one-way property. Once a time-length world line crosses the surface, it cannot cross it again. How do they work that out? Does it have to do with the slopes? Like right at x equals 1. No, right at x equals 2. dv dx is 1.
Yeah. Oh, yeah. And when the slope is 1, that's like the speed of light, isn't it?
Yeah. And so, what does it mean to cross from positive to negative, but not back?
What about the comment at the end? The light cone structure of this model spacetime is in many ways analogous to that of black hole spacetimes to be considered in chapter 12. in particular in having a surface such as x equals 0, out from which you cannot get.
Oh,
Surface such as x equals 0.
sure yet? No, don't feel bad about not understanding this. So what's if x is between 0 and 1, the slope is blowing up to infinity.
Hmm.
I don't know.
Yeah, I don't know either. Do you think this is something like that warp drive one?
Hmm, I don't think so. I mean, the bit where we draw it probably is. This interpretation part for part C, I think is different.
Yeah. Yeah, that does feel like that's the thing you were looking at right at the end of the chapter. Null surfaces have a one-way property.
Okay, what if we look at the solution at least for parts A and B and see if we at least have the drawing right?
Yep.
Okay.
Yeah, because I'm a little bit suspicious even about A. I feel like maybe.
Okay, so it was important to factor out the dv, it looks like. So curves with dv dx equals 0, curves with dv dx equals 1 over 2x.
Okay, so that's what you drew, right?
I guess, can x be constant? No, it can't. B, oh, what the hell?
Oh,
Oh, the cones are scaling logarithmically, but they,
maybe the problem is we weren't supposed to actually like try and solve for V. Yeah, because for dv dx is 1 over 2x, it only depends on x, doesn't it? So if x is constant, so along a constant vertical line, I guess that means all the little cones should point the same direction.
constant horizontal line?
Maybe. X equals constant. No, I think if I drew a vertical line.
Oh, wait, I think you're right. Okay, I see what you mean now. Yeah.
So in the Oh, so what about that one on the in the solution manual there? Was that at 45 degrees when it was on the v-axis?
Uh, yeah, looks like it.
Oh, I see what you wait. No, I don't get it. Do you understand how they came up with that picture? I don't understand it.
Um,
Maybe it's not quite to scale. You can sort of see that they're getting wider as they go to the right.
okay,
They're
well,
kind of opening up like a Japanese fan or something as you go from left to right. Yeah.
yeah. So dvdx represents a horizontal line, but I agree with your thing that it should be the same for the cone should look the same along a vertical line. And then dvdx is 1 over 2x. So,
Oh, did we get to 2 in the wrong place?
oh, did we?
I don't know. dv
Wait,
2dx is x dv. Maybe they got the 2 in the wrong place. I feel like R2 is in the right place.
let me bring up the errors. Where is it? $7.5. Yep, it's 2 over x.
Oh, is it? Okay, cool. Nice.
Okay, so um dvdx is 1 over 2x.
2 over x.
2 over yeah. uh so if we draw x versus v, if x equals 0, we get a vertical line upward. And so for any v's right there,
Oh,
that's why we get the
that's
90
what.
degree angle there. Okay.
Yeah, okay.
So if I do the thing that they did and just kind of take a constant line of v for part of the border, we'll have another constant line there. And so how do we know it's pointing up and to the left and not down and to the right?
Or any one of those
Oh,
combinations, I
because
know.
it's doing both, I guess. It's just we're caring about the future light cones, I think. The past light cone is the other one. Hey,
Okay,
Adia.
let me catch up with how you work that out.
So yeah.
Is it? Yeah, I don't understand how you know it's up left and down right versus up right and down left.
Oh. Because I looked at the solution key. That's how I knew.
Yeah, I know. I know. I saw it too.
Yeah. That's a good question. Okay, I was thinking about down and to the right, but yeah, you're right. Why isn't it up into the right?
Maybe oh maybe we could pick x equal -1 or something. Maybe that would make it a little more clear.
Yeah, sure.
Because then you get the VDX is negative, right?
Yeah,
So
we'll get -2 for the slope.
so as x increases, v decreases, and we go down and to the right. Maybe that makes
Uh,
more sense.
well, I still don't know why we're drawing the light cone like that versus that. They never really, they just kind of took whatever the smaller angle is, I feel like. Oh, maybe it's the region, so it's the region where it's time-like, not the region where it's space-like.
Oh, perfect. Yes, perfect. Now, how do we sort that
This is
out?
like
So the
shading and
time-like means,
inequality. Um,
yeah, because time-like means what? Your ds squared is negative, right?
yeah.
Yeah, we should be able to sort that out.
Um,
Okay.
V scales with X, and so as X gets farther away from the origin, it gets more time-like. I guess that's my rationale for drawing it to the left and not to the right. I I don't know if that's perfect because the dv and the dx are mixed in one of those terms, but it must have to do with that where ds squared is negative.
So let's say we were in quadrant 1 somewhere, like up here where
Mm-hmm.
they're both but it's dv and dx. Oh, yeah.
Yeah, I'm not taking questions right now. I'm sorry. I'm doing this reading group.
Yeah, what I thought I could see for a second, and I don't think this is true, but what I thought I saw um, was that all these lines were coming down and like meeting at a point. So maybe there's a point somewhere where like the fan is opening, like that, and the light cones are all converging from some point. Does that make sense? So
Mm.
all these ones were going to be constant, but all the ones pointing up were kind of like maybe fanning out from some point here.
Oh.
Would that be true?
Uh.
If dv dx is 2 over x,
I think it just looks like that. I don't know if that's actually
yeah, it
going to
just
be
looks
true.
like that. Yeah, I think you're right. It just kind of looks like that. So now that we got the picture right, what about part C? Show that a particle can cross from positive x to negative x, but not the other way.
That's because a particle's future light cone. Oh wait, lies entirely, like it always points to the left no matter what. You can never move to the right, or at least, well, you kind of can move to the right, but
So you're saying even if I
hmm.
was over here somewhere, my light cone might look like that. And so I could come in. So if I come in from here, well, wait, couldn't I go like this?
Yeah, so
If this is my,
you don't have to cross. You're not forced to cross. If you do cross, though, uh,
oh, it's because of this border. Oh,
yeah,
wait, I see. It doesn't matter about over here. It matters on the v axis here.
you'd have to move faster than light to cross the border to the to going from left to
I
right.
I think I got you now. So it's just this one light cone here, which is very particular, isn't it? Because it's like got a 90-degree angle at its base. So if I try and ever cross, let me see if I get it. So are we kind of saying there's more light cones here, like this one and this one here?
Yeah,
These are all like little light cones on this axis. And so if I come along from the right to any one of those, as soon as I come in, I can no longer get back out because because this is like a fence here.
Mm-hmm. You'd have to
Okay,
like
cool. I mean, I
update your
think we,
diagram for like, because like, I'm imagining like the cone, like you can always extend these cones and draw them as long as you want. We just draw them short for convenience.
yeah,
I'd imagine if once you do cross over this board, you'd have to redraw how your light cone looks
yeah.
and update that.
Wait, redraw it? You're saying if you'd have to redraw the light
Oh,
cone?
like I was thinking like if I were to take this light cone on the right and just extend it, if the particle actually did cross over, I think
Oh, I
like
see. I see.
you can never have that region again, so you'd have to like redraw it to make it more
Yeah,
accurate. Or yeah,
yeah. I
yeah.
got you now. So they're sort of all little infinitesimal light cones at those points. Yeah.
I guess so. Yeah.
We just draw them big enough so we can actually see what's going on.
The
All right.
solution key is
Well, I
very
mean, we
brief
got,
on that, but yeah, I think we got it.
yeah, we were sort of on the right track a little bit with that.
Yeah. Okay. Which one is next? All right, number 10. Okay. Observe moves on a
Oh, this is
curve.
exactly that one I was asking
Oh
about
yeah,
before.
that we couldn't find the transformation.
Yeah.
I did notice the solution for number one or whatever one we had to find the transformation. It said you normally just have to guess and check is like the general technique to find it.
Oh,
um,
moves on a curve x equals 2t.
what are the components of the four velocity? It says curve a time like one. Where did they get four velocity in this chapter?
I think 4 velocity was chapter 5.
Right.
They were talking about it a little bit in section 7-8. They said the time-like vector E naught with the hat is the observer's 4 velocity U observed. Page 154.
Right. And they stated that fact some in like chapter 5 too at some point.
Yeah, towards the end, and I hadn't read that very carefully.
Okay, first question: how's it possible there be a four velocity if our metric only has two things in it? Or how do you have four velocity in two-dimensional geometry? I guess the other two components are always zero.
Yeah, you're right. This says it's a two-dimensional metric. Two-dimensional geometry. What are components of a 4 velocity? Yeah, let's just let y and z be 0, right?
I guess so. Yeah.
Yeah.
Um. I mean, in the example where this metric comes from, they got the... Oh, they use a different world line. What did they do with it?
Yeah, that's just what I was about to say. They had the hyperbolic cosine there, and they used that to come up with some kind of a transformation to find the tau or whatever. Do we have to do something like that? Maybe we do. Isn't that what they did in chapter 5? They got everything in terms of the tau.
Yeah, that was something that they did.
Yeah, yeah. Yesterday I started reading chapter 4 again, or a couple days ago, and then yesterday I was going to read more of it, but I was caught up with a friend and I got stuck doing that.
Mm. Um, it does kind of feel right for the 4 velocity to be in tau, or like I think we would need things to be in tau to find it.
I swear I just did. I had no idea what was going on in chapter 5.
Ooh. Okay, yeah, the definition of the 4 velocity, it's the derivative of each component with respect to tau. So dt d tau, dx d tau, dy d tau.
Okay, so we better tauify it.
Yeah.
Tauify it.
Um, and so wait, well they might tau. Did they tauify it for us? It's the
They did?
technical term. They might have. T equals tau over a, so x of tau. Aha.
Well, wait, wasn't that only? I thought T was tau over A
Oh,
only for our.
for
They had a
Kosh.
different world line.
Yeah, we have a different
Yeah.
world line. How do we do this conversion again?
Oh wait. Oh, I think they just plugged it in. Wait, you just take this and plug it in here,
Take what?
and then do the dx and plug it in here, and we get everything in terms of t. I think that's what they did. Let's.
Yeah, because d tau is minus ds.
Yeah, let's try this. What did I just do?
Oh, you might hit the background thing or something. The opacity, maybe.
Yeah, I know. I made it gray. I didn't mean to do that. Sorry about that. So 2t. Can I just say dx is 2 dt?
Yeah. Okay. Yeah.
I think that's legit. So now this is 4 minus 4 t squared. So square root it? Is that what we do now?
Well, this is ds squared. D tau squared is minus ds squared.
Negative. Okay, so, I got you. So, oops.
And now I think, yeah, we square root it, and I guess we integrate. And that's our conversion.
Can you read my tau here?
Yeah. Is that integral? That should be something simple, right?
So where do we integrate it? We just have to integrate it like you said, right? So, okay, so I don't know. Do you know this one?
Oh. That's not simple as I thought it'd be.
Is it just
It feels like there should be something simpler. Wolfram Alpha is telling me it's like a half root x squared minus 1x plus inverse hyperbolic tan. I was
Holy crow,
expecting,
really?
yeah. I thought it'd be something a little simpler. When there's an alternate form.
They did say t greater than 1. Does that help us?
Make sure we're not taking the square root of a negative.
Oh, yeah.
No, it's just kind of. I see one with arc cinch. That's a
I
little
never
bit
remember
simpler.
these. If it's minus
Oh wait,
1.
that's x squared plus 1.
Yeah. So we let t equals secant? Is that the way to go?
Yeah, we would want secant. Oh, I'm seeing someone suggest a hyperbolic sub. X
Yeah,
equals
let's go.
cos u.
Let's go. Yeah. Does that work?
Uh,
I really wish I knew hyperbolic stuff better.
yeah, same. Apparently, cos is a good idea. I need to look up what that
Oh,
grand.
okay. Okay, let's go. Cos, you said?
Yeah. Cos minus sinh is 1. So yeah, okay.
Cos squared minus 1. Yeah, what is it? Cos squared. My handwriting. Sorry, when I start going quick, I make a mess.
Yeah, that's the identity.
So sinh squared. So this is. And what's the integral of sinh squared?
It's a good question.
We do the same thing, like 1/2 of 1 plus
Oh, yeah.
cos 2
There's
theta
a
or something. Does that?
cos 2, cos 2 theta minus 1 all divided by 2.
Yeah. Wait, you got it
I
on
can
screen
write
there.
it.
1/2 cos minus 1.
Cos minus. Yeah. Oh yeah, and then you just cancel. Okay. Yeah, that looks good. Wait, cos 2 theta.
Thank you. I need a plus c. We can let it equal 0 or something, can't we?
Yeah, they usually just kind of make it 0.
Because if theta is 0, then we want tau to be 0. So yeah, okay. I don't think we need that. So
I guess this is where we're gonna get the inverse
now what?
stuff when we unsub.
Yeah. So we got to unsub, is what you're saying. Okay, so. Oh.
Hey, Ninja.
And what's our identity for sinh 2 theta? Is it 2 sinh cos? I think it is.
Yeah, it is. Oh, nice. That'll.
And so the cos was t. And so the sinh will be what?
What is, yeah, what is sinh of inverse cos? Does that simplify?
Yeah, I think so. I think it's just the square root of 1 plus t squared. Wait. Let's write this again. Cos squared minus sinh squared equals 1. And we want this one to be t. This is pathetic. Okay, wait. This is, let me write it like this. Don, how's my handwriting? Is it acceptable?
No, this is
Can
fine. It's
you can read
readable.
it?
Yeah.
All right. Okay, so now I get t squared equals, so if I want, oh, couldn't I say sinh equals, couldn't I just do this?
No, Joff, yeah, it's physics.
Okay, so that, and if I put in t, so I get t root t squared minus 1.
Oh, that's what you're doing with this. Okay.
I think that's right.
I think that's basically the Wolfram answer. This looks similar. Oh wait, but don't we need? Wait, we want to
Yeah.
invert. Like we want t in terms of tau, though, don't we?
Did I go the wrong way? I
No,
thought
no,
we
no.
wanted tau in terms of t.
I think it's what we had to do, but I just realized how are we gonna get this? Like, we have tau in terms of t. How are we gonna get x in terms of tau? I guess. We can't easily invert this.
Well, if x equals 2t, can we let t equal x over 2? But that's still not what we need, what we want, right?
I guess not quite. Hmm. I was hoping we get a simpler result for the integral.
Yeah. We might be doing more work than we have to here.
I'm worried about that too.
Yeah. So it feels like x equals 2t is a particularly simple curve.
It would be, but it's still going to be warped by the way we're measuring distance, I think. But like, we can't just say that it's moving at the speed of 2 or something like that.
Four velocity is the four vector whose components are the derivatives of the position along the world line with respect to the proper time parameter. Isn't there an easier way for us to find proper time?
I thought this was the process to find it.
Yeah, I thought so too. You know what they did say though? It goes back to that question I was asking at towards the start of, they said this metric is the regular metric in disguise somehow.
Mm-hmm.
This metric is really just flat space in a different system of coordinates. Um,
Maybe just a little peek at the solution to see how they start it.
If you want, if you want.
Okay. Just a little peek. Okay, they do start it the same way. They get the same relation between d tau squared and dt squared.
Okay.
Oh. Okay, so I haven't. They do not integrate it though.
They just said the curve is time-like for t greater than 1. Oh, that
That
makes
makes
sense.
sense, yeah.
Oh, wait a second. If we have no,
We just need to know that, yeah, the as long as it's always positive, that's the only thing we need to care about, I guess. For the time like piece.
so okay, so anyway, I wrote like 10 lines worth of garbage. It looks like we only needed like the first 3 or 4 lines, right?
I thought we needed it,
So
but yeah, it seems that way.
once we got it to here, can we just like use this and get like t d tau or something and leave it in terms of capital T? Can we just do that?
Oh.
Doesn't that give us something? Is that all we need? What's dt d tau again? Is that ds or something?
dt d tau. That should be the time component of the 4 velocity, just right there. Oh my god, that's probably what we do.
Well, how are we supposed to know that that's all you got to do?
Um,
I remember in chapter 4 they said d tau squared is negative ds squared over c squared. That's when we still had c. Oh, well, wait a second. No, we've already used that. Yeah, I don't get it.
okay. Let me from like this step here, I just want to
Do you want me to erase some of
try.
this
No,
garbage?
I mean, you can if you want, but it doesn't hurt to be there. Like
Yeah.
theoretically, dt d tau is I guess 1 over that.
Okay.
We just if I just let it be in capital T. I'm curious if we also know dx is 2 dt.
Oh, you're about to use the chain rule or something, aren't you?
I was just going to kind of mindlessly plug it right in, like 2
Okay.
dx d tau. I hope that's okay. I don't really know. The check I wanted to do is if it dots with itself to -1.
Okay. Is
Because
that a
that
2 or a 1/2 there?
ooh, it's the 1/2. You're right. Hey, Ragav, Chandu. You mean the flag that's always been there? Because if this thing dots with itself to -1, I would feel a lot better about this. Because that is a condition that U has to always fulfill. It's not the arrows. It's this stupid thing. So we get 1/4 with a negative t squared minus 1 plus 1 over t squared minus 1.
Okay, you lost me. How'd you get that dot product there?
Okay, I guess I should say I'm saying u is equal to 1 over 2 root t squared minus 1, comma 1 over root t squared minus 1, 0, 0. And then when you do the dot product with 4 vectors, the time component gets a negative put in front of it randomly. But I basically did this times itself with a negative plus that times itself.
So you're saying like this came from dt tau, and this came from dx d tau.
Yeah. And as a sanity check,
Okay.
I'm hoping we get -1 out of this. I'm not sure that we really are, though.
It would have worked if we still had that 2 here, wouldn't it? If that 2 was still there.
Well, that would give us 0.
Oh, sorry, we're looking for 1.
Um, 4 over 4 t squared minus 1. So we're getting not -1. We're getting something with a variable still. Okay, so I did something wrong. I was not cooking like I thought I was. Maybe, do I need to be more careful with the chain rule piece? Because I feel like the dt d tau, that feels okay to me. Dt, or dx d tau is equal to dx dt dt d tau. And dx dt is 2.
Yeah, that seems
dt
okay.
d tau. Oh yeah, okay, no, that chain rule was okay. So the dt d tau was wrong, evidently. It might be right. We just maybe we should have it in tau and not in t. Maybe it's just the variable choice that's wrong.
We're close. We got to be close.
Yeah.
All right. Yeah, it's just a chapter 5. This is a chapter 5 issue for me. I didn't understand chapter 5. Chapter 5, he said at the start of the book, he's like, well, don't worry if you don't know your special relativity, because it's going to be self-contained in chapter 4 and 5. But I feel like chapter 4 and 5 was just too much of a whirlwind for me.
Yeah.
In particular, these 4 vectors, I just didn't, especially when it got to like momentum and stuff, I was like, no way.
Yeah. One more peek.
Yeah.
Wait, we got the right answer for dt d tau. And for dx dt.
Yeah.
Why doesn't it dot to
okay.
-1? Maybe it only dots to -1 if it's in tau, and I maybe shouldn't have paid attention to that check. Okay, I'm gonna rewrite what I put. Okay. Okay, so we've answered part A, which is we found the components of the 4 velocity. I guess we could write it explicitly.
Oh, it says, is the curve a time-like one? So when you were talking about that dot product being -1, is there some kind of stipulations on that? It says here the 4 velocity is always a unit time-like 4 vector.
Oh, that's only holds for time-like. Well, this is time-like. T tau we said is positive.
A particle follows a time-like world line through space-time. Oh. So basically this chapter 5, where they were doing this, they're assuming time-like world lines. Is that what's going on?
Yeah, we do have a time-like world line, though. That's the other part for part A. We said it is time-like.
Okay, yep, because capital T is greater than 1.
And so it should be true that u dot u is -1, but that's probably only going to happen if things are in tau. That's my assumption.
It's only going to happen when?
If you have the velocity, the 4 velocity in terms of tau.
Yeah.
Because, yeah, I don't know. Was that everything for part A, though? I'm going to peek further. Okay, yeah, that was everything for part A, without reading anything about part B. What did I do? Oh, it's over here. So what about part B? Components of an orthonormal basis E0, E1 for this observer.
I just noticed your microphone's cutting off just a little bit again.
Oh no. I'll get closer to the
barely.
mic. Okay.
Barely. When it says E0, E1, is that supposed to be E0, like 0 hat and E1 hat? I think so. I think that's what they mean.
Oh, I guess so. Yeah, they were using the hat for orthonormal things. That seems sloppy for them to not put hats there.
Yeah, let me check the... Oh, yeah. Which question is this? Problem 10?
Yeah.
Yeah, it says part B of problem 10. The vectors should have hats on the indices. E0 hat, E1 hat.
Oh, the error thing says that?
Yeah, I'm looking in the error thing.
Nice.
Well, they did say that E0 hat is just the observer's 4 velocity, so maybe that's what we found in part A.
I think that's... I remember something about it being true for the time component.
Except these are supposed to be unit vectors. It's not a unit vector, is it?
They don't have to be unit vectors, I don't think.
Oh.
Maybe. Suppose a metric happens to be diagonal in a certain coordinate system. This would be diagonal, the one that we have. Um,
How do you know it's
huh.
diagonal?
Because we don't have any D terms mixed with each other. We could write,
Oh, gotcha.
yeah,
Yep, I get it. I get it.
minus x squared and 1, 0, 0.
Nice.
And so I'm looking at page like 156 and 158 at example
Yeah.
7.9.
Yeah.
They're saying that we can straight up say E0 hat is the first component of that matrix with a negative and a square root.
And flipped over.
Oh, true.
Yeah, I remember reading that and not really understanding that.
I don't either, but that I can blindly apply it to answer part B.
So is our G00 just the same as this dTd tau? Is
uh,
that G00?
no. G00 is minus x squared, I think. It's the coefficients of
Oh, yeah.
the metric.
Yep. Yep. Okay. Is it minus x squared or x squared? Because I'm always not sure about with this negative sign.
I think it's going to be minus because like
Okay.
the eta, oh god, that's a terrible eta. It had the -1 for the time component and positive ones for the space components.
Right.
So blindly applying what the book did, it'll be negative x squared to the power of -1/2. So 1 over x.
Cool.
Is it okay that this is a variable?
Yep. It's good with me.
All right. As long as you're okay with it. 0. That's just still 1.
Actually, if you look at the next example in the book 710, I mean they did have some with r's in them. So I guess you can have variables in your.
Yeah, it's like the regular like r hat and theta hat, they depend on the position. I think it's the same type of thing. I don't know if we have to do the other components, but just in case. I assume we're just going to take them as one. Actually, no, I feel like we just don't mention these.
Yeah, they just wanted E0 and E1.
Oh, yeah, okay.
In fact, it's two-dimensional geometry, so I think they're just linked two vectors in this case.
Yeah, the phrasing there is kind of confusing. Okay, I feel okay about this. Not knowing why, but...
Nice.
Let's see what the answer key says.
I think it's good.
Okay.
Yeah.
The first vector basis is E0 hat equals U. Oh. Well...
That's right. That's what I said a minute ago. But how could it be U and also this other thing? The first basis vector.
Yeah, because I've seen that they talked about that maybe in chapter 6 or something, that U coincides, or there's some relationship between U and the time component. But like, why can't we just do this? 7.27. What's equation 7.27?
Oh, maybe we didn't satisfy 7.27.
No, we did. G, well, yeah. Wait, is G a constant? Is that what we're saying? I don't feel like it should be.
No, because they did like area and volume elements of a sphere on the next page. And then not all the G's were constants. Some of them were like in terms of R or phi.
Yeah.
Yeah, this reminds me of a couple weeks ago. We got the first two questions right, and then the third one not as good, and then the fourth one we took a dive.
Yeah.
I feel like we kind of took a dive on this one a little bit.
We've crossed through the null surface and can't get back now.
Yeah.
Wish, holy crap, it's been a minute. I did change my name. I hope you've been well. Okay. Where were they doing this? This other technique that we were apparently supposed to use. I feel like it was the end of chapter 6. I was wrong. Was it the end of chapter 5? In orthonormal basis for a simple accelerating observer, example 5.7, page 97.
Hmm.
So they take the 0 component just straight up equal to the forward velocity. The other directions can be anything they want as long as they're orthogonal to each other and of unit length.
Sounds like Graham Schmidt.
Yeah. So what are we working with for... I think it's
This
like
must
Graham Schmidt,
be
but we
what
have
they
to guess
did.
and check instead of using projection. Sorry, what?
I was going to say this must be what they did because they're doing F and G here and like solving for F and G. And I saw that's what they were doing in the answers.
Yeah.
I still don't know why you couldn't get away with that shortcut we just tried.
Me neither.
Be funny if it was two different ways to do it.
Oh, you know what? There's wait, orthonormal. Oh, we need to normalize this, don't we? Does that mean getting it in tau?
Oh, please no.
Okay, well, if we didn't do that, my idea is make perpendicular would just be to like negate the y, or like negate. I shouldn't say the y component. Just take that one and make it negative for the other thing, and I think that would assure orthogonality. Well, okay. I can't promise normal, but if they're orthogonal, this is where I'm confused on they should dot to 0, and I assume we want the 4 vector dot product that includes negatives.
Yeah, yeah.
So those two times each other with a negative. Plus those two times each other. Which I'm getting another negative. This can't possibly be right. Okay, well, scratch that. I still think we should probably modify E0 hat in some way, but how? Unit length means E1 hat of tau dot E1 hat of tau is positive 1. Okay, yeah, because the negative 1 is for normalization of the velocity, I guess. But why are we using normal in two different... I don't know. This is so confusing.
I mean, I feel like our vector for E0 is not even a unit vector to begin with.
Yeah, I agree with that.
Maybe we got to make it a unit vector.
How would that work?
Well, I guess this we could just get rid of because whatever T is, this is just a number.
Don't we need to like compensate for it though? It's gonna scale the entire thing.
Yeah, but that's the thing. It's going to scale the both components. So I think we can just throw it out. Maybe the components are in a 2-to-1 ratio. So isn't it true to just say, let's see, 1/2 to 1 is the same as 1 to 2. So isn't it like this? √5. So if I want to scale it back to 1, I got to divide everything by √5. So doesn't this just become 1/2 √5, 1/√5? Is that a unit vector? No. No. 2 up here. I got it backwards, don't I?
I do think we need to
This is
worry about
twice
the
as much.
T's because it's gonna get shorter the bigger T gets. Like this will only be normalized when T equals 1.
Yeah, but let's say T was radical 101, right? Let's say I let T, just to make it easy, if T was the square root of 101, then when I squared that and subtracted 1 and took a square root, I get this whole thing would just be a scaling factor of 1/10, right? So
Yeah, so
basically
it won't
the
be
vector
normal.
is still...
Or it won't be
Oh, I
unit,
see what you're saying.
right?
I see what you're... Oh, I see what you're saying. Oh, I see what you're saying. Sorry, Don. I get it. Yeah, I got you now. So basically we just what the hell do we do then?
Yeah, right?
Yeah, what the hell do we do then? Because we don't know what T is.
And I think the process of converting things to tau like might take care of this, but that doesn't seem feasible. So is there another option? Ah.
Yeah, I'm confused. I'm
Oh, I just
confused.
noticed like the time too. I'm gonna take a little peek.
Yeah,
Um,
let's see what they did.
basis vector E1 hat is orthogonal to this. This is unit length? How? Oh wait, no, okay. The first basis vector is that. The basis vector E1 hat is orthogonal to this and of unit length.
Hmm.
Let E1 hat equal FG. Orthogonality implies. Oh, where the hell is this coming from? What?
UT and UX.
It's the minus 2t. Oh my, you are kidding me.
What?
If we do a dot product, do we need to include the metric, like like, what the fuck? I'm looking at this. The thing that I wasn't understanding is that why is the 2t squared here? And I
Oh,
think
is that
that's the x squared in the metric, but converted to 2t.
Oh,
I didn't know we needed that. When did they tell us that? What?
I guess. Well, that's the G, right? That's the G00 or whatever.
Yeah, but I really hope they told us somewhere that that's how you do a dot product.
Yeah, they
I'm
did.
actually
Somewhere they were saying that.
okay, because I'm really annoyed if they didn't tell us that.
No, they did. I'm pretty sure I read that recently.
I don't know. Maybe it's in a different chapter or something. I'm not quickly seeing it.
Is it page 155?
Oh,
Scalar product that's in a coordinate basis.
oh. Okay, that is my bad then. I can't be mad at the book as much as I want to be. Okay, so that makes this completely different. Okay, so okay, so we don't. Oh my god. Okay, so the thing that I should have been thinking about when I was doing u.u or e0.e0, I needed to be including the minus 2t squared with the time component times 1/4 times 1 over t squared minus 1 plus 1 over t squared minus 1.
Oh shit! It works.
Does it?
Doesn't that make it work? I think that makes it work. Look, it's gonna
T
work.
squared
You're gonna
minus
get the
1
one you were looking for. Oh, I'll
over
be damned.
t squared minus 1.
Uh,
Uh, yeah, we're getting negative
yeah,
1 here. But that matches with the u
yeah.
dot
That's
u
what you
is
were
negative
looking for.
1.
Oh man, that's great.
Do we have to negate
That's
this, I
great.
wonder? I don't know.
No, it wasn't that what they said in chapter 5? Like the u is supposed to be u dot u is -1 for
Yeah.
time like or whatever. I was just looking at it a
Oh
second
yeah,
ago.
I bet for the time like one it's fine if it's -1. Hey Obi, no, we're learning the hard way that dot products are completely different in this differential geometry messed up world. Well, there's similarities, but you got to include all sorts of different things. Okay. Uh,
That's clear. That's good. I like that.
okay, yeah, this is a breakthrough.
Yeah.
Because now I think I at least I think we know what to do. So we need to we're gonna temporarily say that E1 hat is something is like F comma G is what they were doing. And now we can get two equations and two unknowns. Because it should be true that E1 hat dot E1 hat, which is include the metric. Don't forget the metric. 2t squared f squared plus g squared is 1 to be normal. Hey Bumbo Crepes, welcome in. I should give myself some more room here. So that's one of the conditions for normality. The orthogonality condition gives us, I don't think order's important. Minus 2t squared time component of E0. Times time component of E1 plus 1 over root t squared minus 1. Nope, that's squared the stuff. No, I don't square it. I don't square it. Never mind. Sorry, what?
I was wondering which one you were about to square. That's all.
Oh wait, but yeah, that shouldn't be squared then. Or no, yes it should. Should it?
I think it should. Yeah, I think it should.
Yeah.
Okay, so let's see what we get.
Okay, so solving for f and g in terms of t.
So
Or
these,
t squared f squared plus g squared. Oh, you just want to eliminate them? I like that.
yeah.
And so what is that? We're gonna get trying to do some amount of mental math.
Solve for G.
Minus 2 t squared f plus g.
Yeah.
Not 6. Okay, yeah, just making sure that I did that math right. Okay. And like you said, we can isolate G.
Sub it in.
4t squared f squared plus 4t to the
4t to
fourth.
the fourth f squared.
Aha.
Ah.
That seems like a thing.
Yep.
Which means G is 2t squared times f. So we just get t over root t squared minus 1.
Okay.
Theoretically, we can say ta-da. I guess we can factor the 1 over root, or the t squared minus 1 out. What do you think?
Yeah, I like it. I like it.
Can't wait to figure out what small algebra mistake it made here, but I think this is the process at least.
I didn't see any. I was watching.
Okay. I guess let's see what the solution says.
Yeah.
Oh, I think we got it.
1 over 2t comma t. Yeah.
Oh my god. Okay. Well, lesson learned with a dot product. Gotta include
Yeah,
the
you know.
coefficients.
Yeah, I was reading about that you had to use the metric when you're doing the dot product, and I didn't even think about it.
Yeah,
When
that
you were doing that previous calculation you did over here, and we weren't getting the -1,
and
and
that's why.
I didn't even think of it. Didn't even think of it.
I was just chalking it up to having to be in terms of tau, but I guess not. It should hold for whatever the parameter is, or maybe certain types of parameters. Okay, well, this went better than I thought it would go. I gotta say.
Excalidraw is complaining that it couldn't save it to the database.
Oh yeah, I
But
got that a
maybe
while
you can
ago.
still...
Yeah,
Okay.
you can still like save it locally. You just like can't come
Okay.
back to it another day or anything. God, what a journey number
All right,
10
well,
was. A couple of these were.
yeah.
But yeah, nice work.
Yeah, it was cool. I feel like I learned something.
Yeah, honestly, it's probably been better than chapter 6 in terms of like being able to answer the questions, so maybe it's not that bad. All right.
I was talking to Poison Mouse before in Dawn's, not Dawn. I'm saying I'm talking to Dawn, and sorry, in Zach's. We were watching Zach's stream,
Mm-hmm.
and he was talking about reading a book on electricity and magnetism. So I asked him which one, and he said Griffith's, and then he said he wanted to
Oh,
read it. So,
yeah, we were talking
yeah.
about that the other day. Me and Mouse.
Oh,
Yeah, it'd be cool to dig into Griffith sometime.
yeah. Maybe we'll try and set something up, he and I. So
Oh, nice.
if we can, if you're interested, I'll let you know.
Yeah.
Or then again, it might just be biting off more than I can chew. So
I still want to read the last few chapters of the Purcell book, and I never got around to it. But yeah, E and M, I really like that. Like I want to learn it deeper.
yeah.
But
All right. Well,
day.
thanks for having me again.
Thanks for being here. I guess we'll plan for one more meeting on this, and then pushing through for the week after next.
Nice.
We got about a little less than halfway through the questions that I chose, and I thought I chose way too many, so that's pretty good progress.
Good.
So yeah, I'll see you around.
Yep. See you, Don.
All right, bye. Okay. What music are we playing? I didn't even notice how much overtime we went, but there's no rules. So yeah, Bumble Crepes, welcome in. Sorry, it's sometimes hard to interact with chat in real time when we're doing these groups. I'm going to take a minute to switch things over to just doing a regular math stream. Really? You don't change the category? Akbar, welcome in. Interesting, unique live. You're actually very early career scientist working in 21 centimeter cosmology? Or 21 cm cosmology? Maybe that's not centimeter. High school physics and math teachers. Interesting. Oh, that's amazing, Akbar. So yeah, the theme of my so like the default theme for my stream is I answer people's math questions. I have a bachelor's in applied math. I'm going to change my YouTube info right now. But on Saturdays, I've been doing these reading groups for general relativity. Where me and Fenbox are basically learning this for the first time. And we're just talking about the material, working through problems. They're only supposed to last about 2 hours. We went pretty overtime today, but that's because we were having fun. Okay, YouTube info is updated now. Yeah, nice. And so yeah, if you're interested, I'm not the only one who does like streams like these on YouTube. There's Actual Education, aka Dr. Gold. He's a friend. He's got a PhD in physics. Actually, his stream is more targeted towards high school, like science and math. But if you're interested in like channels like these, he's another one. He's another one on YouTube, and then I dual stream also to Twitch. And over on Twitch, there's a whole like little niche of people who do stuff like this. What am I writing here? Chapter 7, Part 1. Damn. Tough problems at the end. Oh, for like today, yeah. But I think that was a pretty instructive problem for us to work through at least. That struggle felt worthwhile. CM in centimeters. Oh, okay. Oh, radio cosmology. Okay, so you're referring to like the wavelengths. That's awesome though. I would love to know more general like astronomy and cosmology stuff. There's a bunch of things that I'd love to do a written group like this on. Nightbot link. Oh, seriously? Oh my god, it does. Yes. In YouTube, I never updated it. Oh my god. Thank you, Phobos. Where's that command thing? I want to do it now before I forget. Not that. Wait. Oh, that's Nightbot. Duh. I was happy to find flaws and stuff. Oop. Please do. Okay. How the hell does Nightbot work again? Now that's logged into Twitch. Maybe, I don't know. Yeah. Who cares? Dude, come on. Hurry up. Yeah. I don't know why I need to do that all the time. Commands. Wait. I guess that's it. I haven't updated this shit in so long. I should really just I phased out Nightbot from Twitch. I think almost entirely, if not entirely. I should really do that for YouTube too. I'll get around to it someday, I'm sure. Come on, Nightbot. Nightbot's so slow on YouTube too. It really takes its time to think about it. There we go. Okay. $10 asked for overtime payment. Oh, hey. No, oh no, this isn't the song. Never mind. Okay, let me just read what this one DM is. I'm not showing my Discord, right? I'm not. Okay, I'll get back to that later. It's still a good song, yeah, but it's not the song. Oh, I can see the song though. It's just like 4 or 5 songs later. Okay, let's see if my eyes can handle the light being on. I turned the light off partway through because it was just like bothering my eyes, but they feel better now. MMD, hello? HM, am I in the UK? No, I'm American. Oh, you're MMD? Yeah, Obi's in the UK. The song? Oh. Wait, is that on their new album? I don't remember the... Okay, yeah, it is. Wait, Poison Mouse, if you're MMD, you've seen my stream, you've been watching for a long time, haven't you? I feel like I've seen MMD around in YouTube chat for way longer than I've seen you around in Twitch chat. Oh my god. Well, yeah, I know Poison Mouse is Mataratos in Discord, but I didn't know that he was at MMD on YouTube. So Poison Mouse has been watching the stream for a lot longer than I realized, which is always cool to learn. So many disguises, yeah. What are we gonna do? You have a long tail. Just A-level maths. Oh, uh, yeah. I've been trying to learn general relativity. The normal stuff that I do is way simpler and not so complicated and like annoying. Ask Fever? Who's Fever? Your cousin. Let's see. I don't think I've ever heard of this. It's a movie. That guy looks familiar. I can't zoom in. I think I've seen that guy maybe. All right, but what should I don't know what to work on. People wants to travel to America for the American dream, then he gets lost. That is the worst Phobos. Yeah, it gives me a smaller version. I could code something. I could. I hate starting or like the worst part about coding is like coming back from a break because you have to relearn stuff. We could look for an interesting Project Euler question, I guess. See if one inspires me to try and write some code. Oh, I'm gonna sign in again. 1 second. Why is that autofilling? What's my password for this? Oh, I got it right. Look at me go. When you click on the feet and they're more pixelated than the original. I hate it, you know? That happens to me all the time when I'm perusing feet pictures. What big feet mean. Maybe we'll sort by difficulty. I don't know. Other difficulty. What's like a 10%? Under the rainbow. That sounds appealing. How many problems have I solved? How do I see that? Uh 22? Oh, yeah. I can I used to do this on stream all the time. I haven't done it for a very long time though. 103. Oh yeah, I think I saw you doing that. And I just saw you today doing something like binary trees or something. The math concept is 70 different equations. Those equations make another equation which reveals a price. What? Like a system of equations? Maybe, yeah. 70 color balls are placed in an urn. 10 for each of the 7 rainbow colors. What is the expected number of distinct colors in 20 randomly picked balls? Can you do this? This is just a math question, isn't it? I don't feel like you need to code this. It's probably complicated to do by hand, though. Oh yeah, they are all math questions, but usually you can't do them by hand, or they're not, like, you do some work by hand, but then you need to write code at some point. This feels like you could do it all by hand if you cared to. But your probability is for getting a certain color is 1 in 7, right? Distinct colors are hard by hand? Really? Okay. I suck with probability is the issue. I don't know how you would solve it by hand. I think coding it would be pretty straightforward, though. Trick question, urns are for ashes. Bilo, I like the way you think. Do you guys enjoy looking at black screens? There we go. That's better. Okay. Which number is this? 493. Oh no. I hit make new file. Oh no, what did it call a new file? I can't live with there being a randomly named, like, new file with a crappy name. Where would it be? I don't see it. Hopefully it just deleted itself. Default name for VS Code is blank. You press enter. Okay, good. I mean, I didn't press enter. I just clicked away. Okay. 493. 493. What's my naming convention? Okay. What? Hey, bad. PE493.py. If you version control this. I am completely ignorant of how you use IDEs and Git and really everything that makes coding easier. It's 40? That's not 70. You need to feed Femvox fan. I'm sure he'll appreciate that. Use an editor like Vim without plugins. Okay. Oh, in 20 randomly picked balls. Picking those balls. So, can we make life easier and just do 7 colored balls, 1 of each color? Like, I feel like that's completely equivalent here. Oh wait, no. It's with, is it with or without replacement? I guess it's without replacement. That's what makes a difference. Echo number. Wait, what does that do, Phobos? It's how elite coders code. Okay. Do I put that down here? If it doesn't exist, it creates that file. Save it first. Okay. Oh. 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 Funny. That's kind of that is pretty magical. No editors needed. I guess not. It's the dream. I like being able to hit tab and have it complete things for me, though. Okay, first question. How do we make an array in Python again? See, this is why I hate, like, is it brackets? Wait, okay, I want 10 7 times. Surely there's an easy way of doing that. Besides writing out 10 7 times. Okay. For, oh, how do you do a for loop? I don't remember how you do shit in this language. Oh, okay, there. Thank you, Phobos. List range 1 8 times 10. So what is this? It makes, what does range do? Wait, isn't this doing like 1 2 3 4 5 6 7 8? I guess we can. Wait, what? This would work with like a NumPy array, I think. I just want to represent the urn as an array with 7 10s. That's what I was trying to do right there. Oh wait, but okay. Oh wait. Oh Slim, you're doing the fancy. Oops, I forget what that's called. Dude, what I'm messing my entire life up right now. I for I in range 7. List comprehension. Well, that's not right either. Oh wait, that's the song. That's what I want. You hate Python? I'm not a big fan of it. It's okay though. Um, we should. I'm gonna put another for loop outside of this, but we'll do that later. So what am I trying to do? I want to generate a random number from 1 through 7. And I want to subtract 1. Wait. Yes. Yes. Okay. Yes. Um, how do you do random in Python? I need to be coached on every single piece of this. Okay, sleep well, mouse. Bye. I need to import random. What do you do? Tell me the documentation. I'm lost. Oh. In range A, B inclusive. Okay, good. You never seen those stars in the autocomplete? Oh, are they like favorites or like most common? VIP methods, I guess so. Okay, good song over. Back to normal volume. Uh, while earn of color is equal to 0, keep making new ones. Earn color minus equal 1. And now we're going to count how many of these are no longer 20. 10. 20? 10. 10. Okay. Go. Ah. For I in range earn dot len? Len? No, wait, is it length earn? No, it's earn dot len. Why len? I hate len. No, not that. Wait. Just, dude, I hate len. And do I probably need a -1. I hate the underscores even more. I just hate both conventions, I think. Or I hate both ways that Python does the length. If earn I is not equal to 10, then distinct colors plus plus. Oh my god, Python, you don't do that. I can't believe you. What did Len killed my family. Okay. This is a single simulation. For sim in range, I don't know, 1,000? Actually, we should make that a parameter or a variable. Because we're gonna need to average it. Uh, distinct colors. I think I'm off by wanting my range calls in the wrong direction. Oh, the stop is exclusive. Bruh. So does that work? Okay. Oh wait, so you know, I don't even need this distinct colors. Wait, do I? I don't think I do. Can I just do that? And then at the very end here, print distinct colors divided by num sims. Is that a thing? Bruh. Oh, this is inclusive. That seems like a reasonable answer. It seems really weird, yeah. If you pick 20 balls randomly, there should be a very high chance that you get all 7. They're asking for 9 digits after the decimal? Why is this so exact? Is it getting rounded, or is that just... I feel like they're rounding it. Can I make them not round it? Simulate harder? Harder! Harder! I don't know if I want that many. Oh, I might have simulated too hard. I just noticed that when I divided by 1,000, it gave me 3 decimals, and when I divided by 10,000, it gave me 4 decimals. I feel like it has more decimals to show me. Really? Oh, you're right. That does make sense. Right, it doesn't have more decimals. So I'm probably doing a poor job of optimizing this. Let's see how long this takes to run. I should have made it update every so often. Like print something out every like 10 to the 8 lines or simulations. Okay, let's... If sim mod 10 to the 8 equals 0, print... Oh, what a string. It's a string concatenation work the way that I want. Oh. Okay, thank you, Phobos. Forgot about format strings. Format strings are pretty awesome. Colon 0.9f. Right, I have to do this stupid thing. All right, this seems like it's running a little too slow. Do it by hand and race the computer. With how bad my computer is, there's a solid chance I could beat it. But between both my aging computer and my poor coding skills, I should say. So we presumably have to look for a simplification here. Well, what can we do? As soon as we've pulled 7 things, we don't need to keep going. That's something we can do. Or as soon as we've touched each color once, there's no point in continuing. I don't think that's going to be a particularly big gain, though. Okay, this thing is never going to complete in a reasonable amount of time. Len set random dot sample list range. Oh my god, what's happening here? Um, wait. Oh, we're sampling it 20 times. Oh, I see what you're doing there, Phobos. Can't that choose the same color more than 10 times, though? Gotta run? Okay, no worries. See you around. Thank you for your help. Lubert, you did it by hand? Wow. How do you do it? Both ideas should return 7 when you get 7 different colors. Well, I'm concerned that it could return, like, the random dot sample, it could take 11 out of a particular color, and that's just a different probability distribution, right? Whereas we can't go more than 10. Set doesn't have duplicates. No, I'm not talking about the part with set. I'm just saying that the sampling method doesn't match, or like, I assume the way that random.sample works is that it's just gonna, I mean, I know the set part is to remove the duplicates, but I'm just saying we can't allow for a possibility of there being 11 of the same color pulled, because that's just not the situation that we have. But the random.sample is potentially pulling 11 of the same color. With replacement or without replacement? Oh, really? K unique random elements. Ooh. Wait, what is K? K unique random elements. And so is counts the population size of each? So if we include counts. Oh, we need to include counts. We can do that. Okay. I really wish Python had block comments, man. What am I gonna do here? We can just delete all of this, really. Let's comment it line by line. Resident sleeper. Okay. Do it up here. Distinct colors plus equal len set random dot sample list range 7 wait times 10. So 20 is the number of things that we're choosing. Then we need counts equals 10 for I in range 7, k equals 20. There. Question mark. The number of counts does not match the so well, that doesn't matter. If I come up here, print, I'm still suspicious of this list range thing. Okay, yeah, the list range thing isn't doing what I want it to. So instead of this, we'll just do oh wait, we don't need to do that times 10. Can we just do that 0, 1, 2, 3, 4, 5, 6? Let's see. How to become good at math, Loki? A lot of it is just practice, unfortunately. Just gotta kind of grind it out a lot. Okay, so this is a lot shorter. It's still running very slowly, though. I wonder, like, how there must be a mathematical shortcut we can take. Well, apparently, according to Lubert, you can just do the entire thing on paper, but presumably they, like, when they made this question, they had an idea for, like, how you can code this efficiently. Yeah, so let's cut that off. Like, we need to think about a process that's equivalent to the question, I guess. I don't know. Hmm. Looper started with indicator variables. Define x sub I as the random variable taking the value 1 when the ith color appears and 0 otherwise. Then we need to find... Oh, interesting. And expected value is linear, right? So you could split those up into different things if, as long as they're independent. I guess they're not independent. I wish it was better probability. You find that does start to look like a geometric distribution, right? Where you ask like, what's the, well, not geometric, but like, no, the trials aren't independent. We can't do binomial or anything that relies on binomial. They're linear even when not independent? Oh. Holy crap. Okay. Uh, I never cleaned up this file from last stream. It's fine. Depends required for linear variance though. Ooh, okay. So what's the expected value for one of these? Like I expect all these expected values will be equal because there isn't anything special about a particular color. So what's if we just focus on EX1? Out of 20 trials. Hey, Melee fam. It's good to see you. Just to have something to work on, I brought up Project Euler, which is a website with like coding challenges that are based on math problems. And so I'm working on this particular problem here. I'm following along with Lubert's idea that I think can just, it seems like it can just be done with pen and paper and not even any coding. Where I'm at right now is I've written code that theoretically will just simulate it and find the answer that way, but it runs way too slowly. It's never going to get enough simulations to get the answer to 9 decimal places like they want. So I'm trying to follow Lubert's train of thought to just do this with good old-fashioned math and no coding at all. So if it happens on the first poll, that's a 1 in 7 chance. If it happens on the second poll, that's 6 in 7 times 10 in 69. Wait, yeah, there's 70 balls in total, right? So it's probably more clear to write it like to not cancel the tens, I think. Check your Project Euler thing, you solved the problem already. You Monte Carlo'd it. Do you have a supercomputer? 59 and 7 and 69 times 10 and 68. Can we just like, can we express this as a sum? I'm just trying to get a feel for that pattern. So there'll be 19. So 41? Um, 51 times 10 and 50. There's a couple interesting strategies. Don't remember which one to use now. You have a normal computer. It's kind of old. No, I'm just making fun. Hey, Skirtle. If there's games happening tonight, Skirtle, I'm probably not going to go for a lot longer tonight. Games, you say? I do. From I equals I guess 0 to 19. Product let's not do the product. Let's just write it. Is that called the Pock Hammer? I think, I don't know. That's not quite right for I equals 0. I don't have this formula quite right. But, I mean, okay. Even without this, I could figure out a way to calculate this just with code. And I would multiply it by 7, and is that the answer? Exactly? Oh, I didn't even see you put that there, Loki. Yeah, there's quite a few people who ask J questions, and I normally can't do them, so I just started to put that pin there. Seems to be the most common strategy. Okay, I don't know how to express it easily with... Well, I'll just take the first one out as an edge case, I guess, but... let S be the sum, P be the product, R be the sum of the reciprocals of 3 terms of geometric progression. Oh god, yeah, I don't think I know how to do the question you put there. It's not using combinations. Oh, really? Oh, wait, do I need a combinations term? Ooh. Yeah, do I need coefficients for the things that I wrote? Oh, am I okay? Okay. Um, oh, wait, this is just choose. Is that the idea? Just have to find choose in the right way. Is it? I feel like I've seen... The combinations way would make this a lot easier to compress. Yeah, I'm trying to get something I can enter into Wolfram Alpha, I guess. Or into... I could figure out how to enter this into Python. It'd be a little bit painful, though. If I just remove 10 over 70... Because I don't like it. The complement of color not appearing? Oh, yeah. How would that look? Is that just 50 out of 70? No, 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 no. Oh, okay. So, it's 50 out of 70 times 49 out of 69, like that. $31 out of 51. Wait, no. 30 out of 50, because this is all 20. Okay, I still don't know how to express that with combinations, but this is a lot simpler. Isn't this 21 things? Should it end at 31? I feel like it should end at 31, to be honest now. I think it ends at 31. And this goes to 19. That's something I can enter into Wolfram. I multiply by 7. I have to remember that. That's not 9 decimals. I mean, 1 minus. It's still not 9 decimals. Oh, more digits. There we go. I forgot. 997 962 101. 997 962 101. 997 962 101. Not certain you want to start at 50 over 70. Lubert, you were right. I forgot there's 10 of each. Eight one eight 741 802. 818 741 802. 818 74. I lost it. 41802. Isn't it weird? It's easier to remember it's in blocks of 3. I'm sure there's some scientists can explain that, or maybe not. Oh no, wait. I got the probability, right? Question, you want to study in US for further studies like after high school? I'm confused how I should start preparing for SAT along with school. Any suggestions? Not much beyond just kind of like look up resources on Google. There's plenty of things to help prepare students for the SAT. For school in general, it's kind of hard to suggest, or it's kind of hard for me to say that because I don't know like how other cultures think about this type of stuff. And I don't know where you're from either. And if I did, I probably wouldn't know how your culture is different. So, or at least I wouldn't know like well enough to be able to give advice like that. Would I be right in saying probability of x less than or equal to n is equal to 7 choose n over 7 to the 20? Maybe it's something like that. Yeah, I do remember that they give you access to the forum. Once you complete it. So wait, I'm doing 7 times. Oh, what? Excuse me. What? 7 times 1 minus this? Okay, I think that's more like it. Okay, 6, 818, 741-802. That's just like the probability. What the hell? Okay, 6-818-741-802. 6-818-741. 6-818-741-802. Did I actually get that? 818-741-802. Look at me go. Oh my god. All right, I guess no coding required there. Thank you, Lubert. So yeah, we can look into see what the forum says. Why don't they give you a button to go directly to it? You were the 5,947th. Wait, how do you see how many people have solved it? Oh wait, is this the time from when they first open it? I don't know how you see your like rank. Was it on the last screen? I don't know. $60 choose 20 over $70 choose 20. Oh, that's funny, Lubert. You beat me. Wait, so 60 choose 20 is the thing that I wrote here? Huh. Or rather, there's a cancellation that happened, was the trick that I didn't see. Yeah, I feel like I've seen a problem, like someone had given me a problem once that was something to the effect of whenever you have an expression like this, you can make it a quotient of chooses. I just couldn't remember how it worked. So I didn't really try with it. This person using chi and kappa? Oh my god. Dude, all the people calling it easy, shut the hell up. Easy, simple. Simple. Very simple. Simple. Shut the hell up. Okay. Anyway, thank you for the help there, Lubert and Slim. Oh yeah, so Mill A fan, you were asking about the probability. Maths are definitely smug, yeah. 7 choose n times n over 7 to the 20. The problem with n over 7 to the 20, I think, is that you're doing it without replacement. So reducing things to 1 over 7 isn't always right, or it's only right on the first poll. Computer scientists are also smug, so the 4 was an intersection of smug people. It's without replacement. They didn't. I don't know if they actually said that. To be honest, you can give out 5 kudos. I think it was just kind of implied by the wording. They didn't say it explicitly. Yeah, I assume I'm not going to do better than the built-in Python methods that are already kind of as efficient or they're more efficient than anything your average user is going to write, as far as I know, when it comes to like the built-in stuff, the built-in functions methods for this. So I as soon as this didn't improve it, I feel like we have to turn to pen and paper. Where I solved it, probably something similar to the linearity of expectation. Solved it years ago. Yeah, fair. All right. Well, that was a nice little slight return to coding. Tyler seems too computationally expensive. Yeah. I think we'll call it there for the day. It's 4 hours. Yeah, I think we'll call it. Oh, you know what? I got through an entire stream. Dude, my voice is actually improving. I never ate my cough drop this stream. The light makes it impossible to see, but I didn't need it. So yeah, I'll cut the YouTube stream off here. So anyways, here on YouTube, thanks for being here. On Twitch, we'll look for a raid. Yeah. So goodbye, YouTube.